hard. Look at that. I'm remembering everything today. So we talked about cells, how cells can live alone. They can be part of a more complex being, more complex community. They do have this genetic material. We talked about prokaryotes and eukaryotes. Prokaryotes do not have a nucleus, but they do still have genetic material. They do still have DNA. Eukaryotes do have a nucleus. They are an evolved cell. They are a much larger, more complex cell. And they did kind of incorporate that prokaryotic cell into them to provide them with the energy they needed since they were so much bigger and so much more complex. We had a pretty rousing talk about viruses and prions. I think it wasn't in this group, it was in the other group for some reason. You know how we get on these little tangents, and that's okay. Wakes you guys up. Started talking about viruses and prions and zombies. I don't know how we got on the discussion of zombies. I don't know how we get on some of the discussions we get on, but I do sure enjoy them. So there's our picture of our prokaryotic and eukaryotic. Why are cells small? Well, there is some limitations as far as the ability to provide themselves with nutrition, the ability to oxygenate themselves, and the larger the cell, the more nuclei you need. Now, it doesn't mean we don't have cells that are so big we need multiple. No, of course not. Your muscle cells, cardiac cells, they all have multiple nuclei. But the larger the cell, the more nutrients, the more oxygen, the more energy. And so that's why our cells are really limited as far as their size. We talked a little bit about the cell membrane, kind of the skin of the cell. Everything on the inside of the cell is known as cytoplasm, and we're going to be discussing the organelles today, which is on the inside. Those are like the tiny organs, that's what it translates to. And the nucleus, which is kind of the brain of the cell, and that's what contains our DNA, our genetic material. So there's a picture. So the cell membrane, we know, is a phospholipid bilayer. It has hydrophilic and hydrophobic ends. Where is the hydrophilic end located? Yeah, on the outside, the heads, remember the bison, their heads are on the outside, and the hydrophobic are the tails on the inside. Just like our skin, it is capable of repair to a degree, right? If you over damage the cell, obviously it's gonna die. It's gonna be taken out of circulation. And this cell membrane is gonna be primarily, we talked a lot about proteins, we're gonna review those. Some of our phospholipids, big cholesterol, help maintain the shape and allow it to change its shape. So there's our phospholipid bilayer. Hydrophilic heads, hydrophobic tails. And because it is lipid, phospholipid, it means that water-based things have a really hard time getting through. And so they do need active energy to pass back and forth through this membrane. We've got cholesterol that wedges themselves. And these cholesterol is not the bad cholesterol that'll kill you. Like it'll clog up your arteries and cause you to have a heart attack or a stroke. This is really good cholesterol. And it helps to maintain the cell membrane structure and stabilize it. It's called a fluid mosaic because it does kind of have this constant motion, just like waves on the ocean. We had our proteins that we talked about, our globular versus our functional. They also make up some of these channels that we talked about that allow easier passage of things back and forth through the cell membrane. We had our integral proteins. These are using ATP. They actively transport substances. And then we had our channels. This is where we were all going to a concert. You have your selective channels, which is exactly what it sounds like. Only VIP. Very selective, only specific things can pass through this channel. Or we have pores, and literally anybody who has a ticket can come in. That's general admission. You still got to have a ticket. It's not just letting anyone willy-nilly freely passing. You got to have a ticket, but this one's more general admission. There's our picture. It's really amazing that this entire environment is on every single cell. I find that fascinating. We have globular proteins. These are what are involved in changing the shape of the cell. And some of these cells, their shapes have to change really dramatically. I think yesterday we compared like our muscle cells will shrink down by half as far as length, but then they widen. Your cardiac cells, your bladder cells, and your stomach cells stretch and get much thinner and have way more surface area. And it's these globular proteins that help it to change its shape. That would be a great test question. Which of the following proteins helps a cell to change its shape? We'll just start writing the test now. How about that? That'd be a great test question. And then we have to have the cell have an ability to recognize other cells. This is how they recognize stranger danger. This is how we don't attack ourselves. Our immunity group doesn't start just, blasting away friendly fire. And so every cell has this specialized, unique coating called the glycocalyx. It's a sticky sugar protein around the cell. And it is what signals to other cells, yes, I am supposed to be here, or stranger danger. All cells have this, including things like bacteria and viruses. And once our body recognizes that glycocalyx, that's what tells it, yes, it's okay for this cell to be here, or no, we got to launch an attack, stranger danger. And the ability to recognize stranger danger, that's an antibody. We talked about that before. He's got a little wanted poster, and he's looking around for that one guy on the wanted poster, and then he'll say to immunity group, hey, this guy is here, we need to take some action. Immunity group looks up his instructions and knows exactly what to do to get rid of it. And that's all about an antibody. So this glycocalyx is what allows your body to not attack itself. Now, there are some times when this goes horribly wrong, and your body immunity group starts recognizing this glycocalyx as stranger danger, even though it's part of you. And these are immune-mediated disorders. Most common one we probably all heard of. If you've ever watched House, the show House, oh my goodness.
Yes.
Yes. So here's my little tech tip for you. House is one of the best medical shows as far as using proper medical terminology. So if you really want to start practicing your medical terminology, I suggest you watch some episodes of House. A lot of the other shows, like the soap opera kind of medical shows, like Grey's Anatomy, there was a bunch of them back in the 90s, ER, Chicago Hope. Yeah, they don't use appropriate medical terminology, or they dumb it down to the point where it's no longer useful. House, on the other hand, he's just rattling off those med terms, and you just gotta try and follow along. So a fabulous show if you want to practice your medical terminology. It's on Prime. Yeah. I love House. I love that show. I was really fortunate to get to see him in concert.
Really?
He's an incredibly talented musician, in case you didn't know. He has a band called the Copper Bottom Band. And he came in and we went and saw a show at the Alley Theater. It was fabulous. It was so good. Oh, so good. Anyway, it's never lupus, was my whole point. It's never lupus. Well, we've all heard the term lupus, and what lupus is where your body starts misrecognizing this glycocalyx and starts attacking cells that are actually supposed to be there. And so, it'll start attacking your joints, it'll start attacking your other blood cells. It's just a huge oogie mess. So we had a couple of different families in our glycocalyx. Cell adhesion, this is what helps to signal other cells for help. If I find an area of infection or inflammation, I've got to be able to signal other people, send in the backup. And so that's our cell adhesion. The other thing it does is it helps cells move across each other. So we're using our cytoskeleton, which we also started talking about yesterday, and we're using these little pathways. And so imagine if I'm a cell and I'm walking on this pathway, but there's another cell coming the other way. Well, what do I do? So basically what we do is we go and we stick on each other and we just do this. And then we go on our way. And so it kind of helps these little cells move and these little organelles move inside the cell. Membrane receptors, these are going to be for signaling, stranger danger, helps to identify and target bacteria and viruses and tell the immune system that we need to start launching an attack. And then we started talking about the mobility of other cells. We have some cells that have cilia, which act as like almost like a sea anemone, and it crowd surfs stuff. I think we talked yesterday a little bit about COVID. Did we talk about COVID yesterday? Yeah, we usually end up talking about it. Stupid COVID. What happens is, so we start developing mucus in our lungs. It doesn't have to be COVID. Let's not talk about that today. I'm done with COVID right now. I'm so over it. I have these days where I'm just over everything. I hate everything. I'm having one of those days where I just wake up and I'm like, I hate everything about everything. I do. I just hate everything about everything. Was that your day yesterday? We all have those days, and that's okay. We're here to support each other, and we're allowed to have those days as long as we don't let it wallow. I'm allowing myself one day to have a giant pity party, and then I'm going to get over it and just deal with my life. Let's say it's pollen. Let's say you have allergies. And so you've got cilia in your sinus cavities. You've also got cilia in your trachea and in your lungs. And what happens is your body creates mucus and it kind of sticks the little pollen, and then it crowd surfs it, and then you can cough it up or blow it out or whatever it is. It kind of does a tickle in your throat. I have a tickle right now. Causes you, no, I don't have it. Causes you to get a tickle, you cough, or you clear your throat, and then you swallow it, and then it goes down into the acid of your stomach, and then it gets taken care of there. So the cilia, though, are what crowd surf like a sea anemone. There's our picture. And we have flagella. Some cells physically have a tail, and it moves in kind of a rotor-like motion, causes forward propulsion. The only cell that mammals have that has a tail is going to be sperm. Sperm. We've got our flagellum here. Here's the head that contains the DNA. Here's our little mid piece that contains the energy. And then the tail will move it forward on its very dangerous journey to contribute its genetic material to an egg. There are some other cells. Here we've got a little protozoal. We've also got things like Giardia, which is a protozoal parasite. I think we talked about that. Usually stagnant water, and it's a little parasite. He's actually the happiest of all the little parasites because he physically has a little happy face on his back. It doesn't make you happy if you get him, but he does. He looks like he has a little giant happy face on his back, big smile. So he's the cutest of all the parasites for sure, but also one of the easier ones to get. And that's our review of Chapter 3, Part 1. Do I have any comments, questions, or concerns before we move on to our organelles? Everybody's okay? Wunderbar.
Ms. Huff, I had one thing on your site. It's the same way like for last week, the site that you have the testable material, just 3 different parts, right?
I believe so. I'll have to look at
Okay,
that.
thank you.
So I haven't updated this particular, let me turn this down a bit. I haven't updated this particular one yet, so let me go in as soon as I'm finished class. And
Yes,
I will
ma'am, that's
update
fine.
it.
Thank you.
All right, part 2. All right. Let's get you guys over here. All right, so now that we've talked about the skin of our cell, we've talked about the cell membrane, now that's all the stuff on the inside of the cell, the cytoplasm. Cytoplasm contains the cytosol, which is this jelly-like fluid that helps maintain the cell's shape, also provides kind of a cushion and a place for all these little organelles to float around in. We have a cytoskeleton, which also maintains the shape and allows cells to change shape to some degree. We have our organelles, which translates into tiny organs. And what they really do, every cell that has these organelles does have a function similar to us. They have an organelle that functions like a liver. And they have an organelle that functions like a kidney. And they have one that functions like a stomach. It breaks stuff down. They have one that functions kind of like our respiratory tract, moving stuff in and out. And then you have your inclusions, which are just big voids, like big tummies. And they'll run around the cell and they'll just engulf stuff that is not supposed to be there. Or they'll engulf stuff that is supposed to be there if you're having a big issue. So those are the main components of our cytoplasm. And cytoplasm just is referring to anything on the inside of the cell. Sorry, my nose is running. This colder weather has brought in some allergies. Just saying. Holy smokes. All right, I'll give you guys a minute. So, the cytosol is just the fluid of the cell. It's primarily made of proteins. Our organelles are kind of suspended in this fluid. Also has electrolytes and simple sugars. It's very thick and jelly-like, and it just kind of fills up the cell like a water balloon. That's, in my mind, what it's like. It's filling up the cell like a water balloon, help to keep it inflated. There are some things you can do to a cell to promote fluid to go into the cell or fluid to go out of the cell. These are known, you may have done this in medical terminology, hypotonic, hypertonic, and isotonic. These are words that are going to be very important when you get into things like clinical pathology, pharmacology. You have hypertonic, where the pressure on the outside of the cell is greater than the pressure on the inside. It's going to promote stuff to move to the inside of the cell. Hypotonic is just the opposite. The pressure on the outside is lower than the pressure on the inside, and it's going to promote stuff to move out of the cell. Isotonic is the same. Let me give you an example of a hypertonic solution that you may have done before. Promoting stuff to go into the cell. So you get yourself some gummy bears. This is a fun experiment you can do at home. Get yourself some gummy bears. Those now represent our cells. Get you some clear adult liquid. Okay, I got one person that followed me on that. Adult liquid. Clear adult liquid is hypertonic. So it's going to promote the movement into the gummy bear, into the cell. Drop your gummy bears into that clear. Is anyone not clear on what I'm referring to when I say clear adult liquid? You got me. Drop the gummy bears in there. What happens to the gummy bears? They get bigger and bigger and bigger because we're promoting the movement of fluid into the gummy bear. That's exactly what happens here with the movement of fluid in and out of the cytosol. A fun experiment. I did that experiment several years ago. I'm way too old for that now. But I did that experiment for a New Year's Eve get together I was having, and I forgot
I think
about
I'm gonna do
them.
that experiment this weekend.
Yeah, right? I forgot them in the fridge and like found them 3 days, 4 days later, and they were like humongous. They were ginormous. I threw them away.
Sure you did.
I'm a responsible person. I threw them away in my stomach. The cytoskeleton. We have creepy rule of three. I'm going to minimize you guys because you're kind of in my way right now. I love you, but I'm minimizing you. So our cytoskeleton has creepy rule of three primary components to it. Microtubules, which are made of tubulin, which make little tubes, hence the name. These are the largest parts of our cytoskeleton. We have our intermediate fibers, which were the mama bear, kind of the middle. Those are the ones that act as the guy wires, providing stability. And our microfilaments, which are the smallest and most flexible, and they usually gather really close to the surface of the cell and help the cell change its shape. The other thing that these cytoskeleton does is they provide areas for organelles to anchor to. Organelles are just floating around in the cytosol. So let's take one, for example, our mitochondria, the powerhouse of the cell. And I say, oh no, I need some more energy on this other part, this other quadrant of the cell. So my mitochondria just kind of float and they use these cytoskeleton to drag themselves over, and then they just anchor to it. Just like a boat coming into port. That's it. That's all I got to say for that.
Is there like a spider web then?
It kind of looks like a
stick it right on.
yes.
Yeah.
It does kind of act like that, where they can just use it like a tightrope. But yeah, like a spider crawling up all over a web. And then he goes, oh no, there's a bug over there. And then he can use the web to go, and then he just anchors himself. That's, yeah, mentally that's a pretty good analogy. I have a pretty great video over the cytoskeleton. I'm trying to debate whether I'm going to show it to you or not. Yes?
Yeah.
You're saying yes? Okay. So our microtubule tubes, I remember tube sounds big because we got microtubules and microfilaments. A tube or a filament, which one sounds bigger? The tube. That's how I remember microtubule is the biggest of our fibers. These form the cables that our organelles are primarily going to attach to. And the crazy thing is, so they're kind of assembled, they're like little Legos that come together in a circle, and then they can be disassembled and reassembled in another direction depending on what's needed in the cell. Really, really cool. That's it. That's all I got to say about that. I don't even know where Doug is right now, honestly. He may have stayed home. Doug was just like, if you're going to have a bad attitude today, I'm not even going with you. Forget it. Oh, gosh.
Well, we know it's not Doug rebelling today, so that's why you're running off of autopilot, being in that mood.
You know what? Let's blame Doug. It's all Doug's fault. I can't blame him too much because I kind of need him later this evening. I've got a couple of quizzes I got to do. So I kind of need him semi on the wheel. Oh, I usually do. I'll go home and give him a nice nap. He'll be right as rain. Eat a big salad. Our intermediate fibers, intermediate means middle, so these are kind of the middle of the road, the medium. But these are the most permanent part. That would be a great test question. Which of the following cytoskeleton components are the most permanent part? We have two different names, and these names just vary depending on where they are located. Where is the cell located? We have tonofilaments, which is the intermediate fibers in our epithelial cells. And we have neurofilaments, which are the intermediate fibers in nerve cells. So these additional names, we're still referring to the intermediate filaments. We're just saying where is the cell located and what is it doing. So. And then finally, we have our microfilaments, which are the smallest and least permanent. They're going to be arranged in bundles, and these are the things that can reassemble and disassemble, change the cell shape. That's their primary job, is to change the cell's shape. And that'll be determined by what is the cell, where is it, and what is its job. Bladder cell, stomach cell has to change shape a whole lot more than a plain old skin cell. Skin cells do change shape to some degree. Obviously, we've got a little bit of stretch, but definitely not to the same degree that our stomachs and our bladders do. Actin and myosin are two examples of this, and it is actin and myosin that allow our muscles to change their shape so readily. There are these filaments that kind of ratchet over each other and pull the muscle towards the center, causing it to contract. Oh, you guys are still writing. I'll give you a minute. What you guys doing in midterm right now? You just finished your colors?
We're going to be starting on the
Nice.
skeletal system.
You've already started on the skeleton.
No, we're going.
So we're starting that today.
You're now going to start making words.
Yeah.
How exciting!
Yesterday was our last day doing words. That was our last group of words yesterday. We were excited about that.
What's a medical term for white?
Alba.
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 Or Luco.
Luco.
Leuco. Leuco like leukocyte. White blood
Leukemia.
cell. Linea alba. White line.
White.
Got linea alba.
And Albus as well with a US at the end.
Harry Potter.
Yeah.
Is that, yeah, Albus Dumbledore. Yeah, that's how I remember it. Tell me some words for red. This is fun.
Cornell.
Rhodo.
Ruber.
Or Ruber.
Ruber. Ruger. Ruber.
Yeah, that urethro.
Rhodo.
Erythro or something like that is red.
Erythro.
Yeah, we got to color our butterfly.
You got, oh my goodness. That's
Like
adorable.
erythrocyte.
Like red blood cell, erythrocyte. How about, I can't even think of my colors right now.
Cyan, blue.
Cyan, cyano. So if you have a condition of turning blue, cyanosis, cyanotic. Feel free to panic for just a minute if your patient is going cyanotic. Because what does that mean?
They're not breathing.
They're not breathing, they are hypoxic. Hypo-oxygenated. Nice. What is the term for no color?
Is that photo or no? That's like.
I don't think we learned that one.
I think it's no color. It could be every color.
There's one that's
Chromatic.
colors.
Here.
But it's all colors.
Here.
It's colors in general.
All colors was chromo.
Yeah.
All colors is chromo. Because technically it's either all colors or no color. Because it reflects the color. The way that I remember chrome, so a little fun fact about me is I used to be very heavily kind of situated in the biker community. I was a president of an all-ladies motorcycle riding club here in Houston. We have 5 chapters. We're called the Low Riders, Ladies on Wheels. Yep. And I mean, I say biker community. I mean, we would go on Saturday rides to get ice cream or go for a pie social. You know, it wasn't really hardcore. It wasn't all that like the one percenters, Sons of Anarchy, running drugs or anything. You know, we're going and meeting in Austin to eat pie. But it was still a lot of fun, but we did get to hang out with some interesting characters. And Chrome, every biker girl loves her some Chrome. Well, Chrome reflects any color that's going into it. So that's how I remember Chrome. It'll reflect anything, so it's either no color or all colors. Yeah, every girl loved her Chrome. My bike had a lot of Chrome. Still does. Here's our picture. So here we have, let me get so my zoomers can see this too. So here we have our microtubules. Here's another microtubule, the largest of the cytoskeleton, providing a lovely anchor for our organelles. Here's our intermediate fibers acting as that guy wire to provide stability. And then woven up here, those are our microfilaments, and those are what help to change the shape of the cell. So let me go ahead and I want to show you this little video, if I can. Get in here. So this is a little video just over the cytoskeleton. Although I am going to pause. Now that we have an appreciation and an understanding of the cytoskeleton, now we're going to start talking about the little organelles, all of the little structures that cause the cell to be functional. So these little organelles do not have a glycocalyx. Because they are inside the cell itself is being recognized. Some of the organelles we'll talk about, mitochondria, we've used that word 1,047 times. Ribosomes. This is probably a little bit reviewy if you've ever done any kind of basic biology class. The Golgi apparatus, the endoplasmic reticulum, and we actually have two components to that. The smooth endoplasmic reticulum and the rough endoplasmic reticulum, lysosomes, and paradoxosomes. So we're just going to go over each of these structures, what do they do and how do they contribute to the overall working of the cell. Some of them work to provide energy, some of them work to create proteins. They are little factories. Some of them act like a FedEx, moving proteins in and out of the cell. And so we'll just discuss in general their basic jobs and functions. Give you guys a minute. What is the medical term for bone?
Osteo.
Osteo or osteo. Let's see how much you know while everyone's finishing up their notes. What bone is this? That's the humerus. And then I've actually got two bones here in the distal part of my arm. This is where your proximal and distal is going to be super, super duper important. The radius and the ulna. The ulna is what makes up your elbow. Fun fact, you cannot lick your elbow. Just saying. What is this joint right here? The carpus. The metacarpals. Phalanges. What bones are right here? My costo, my ribs. How about this bone right here? My sternum, my neck vertebra, cervical, my chest vertebra. Nice, thoracic. lower back, lumbar, I think lumbar support, and then down here, sacrum. That is the attachment point for my pelvis. You have how many parts to your pelvis? Yep, 3. Creepy rule of 3. You have your hip sassy bone, your ilium. You have the bone, if you lift your legs up and wiggle, the bone you're sitting on right now. That's the ischium. And then the pubis is in the front. So the ilium, ischium, pubis. What about this bone? This is our femur. That's the largest long bone. Little round bone right here. The patella. You've got 2 bones in your distal leg. Tibia, fibula. One is pretty substantial. It's the one that forms your shin. That's your tibia. And then you have one that is very, very slender in comparison. Fibula. The way I remember is you tell a little fib. Tell a little fib. A little fib to who? To you. Fibula. And then this joint, tarsus, metatarsus, phalanges. What is this surface of my foot? Nice. Very good. I think you guys are ready. I think you can just skip the whole lecture and take your test. No. It is the Mondayest Tuesday. I love that.
Oh, I think threw everybody off because we're all used to being at home on Friday. So like, yeah, it felt like a Friday, and today we skipped Sunday and Saturday. Yeah,
I know, right? Oh my goodness. All right, so the mitochondria we know started out as a prokaryotic cell, and it is the powerhouse of the cell. It produces the energy that fuels the cell. And where it produces this energy is right in here. These are called the cristae. And these little folds are where the ATP, or the energy that provides for the cell, that's where it's created, is in these little folds. They can change their location. They're like these big giant slugs. And they just move around the cell depending on where the energy is needed. And they can also divide themselves by fission and make additional mitochondria if called upon to do so. They divide by fission, not by mitosis. Yes, I know I said the M word. We are going to be doing mitosis and meiosis, but mainly mitosis. We're not really going to get into meiosis. But we are going to talk about mitosis, the mitotic cell, anaphase, telophase. We'll get there. These guys, though, don't divide by mitosis. They divide by fission. And it's in this cristae, as I said, where the energy production is, but it's also where we consume our oxygen and release carbon dioxide. These little guys have almost like little lungs of their own. They have to take in oxygen, they release carbon dioxide, and all of that's happening right here at this cristae. And that's the basics behind our mitochondria. They're just big, giant, peanut-looking slugs. So the more active a cell is, the more mitochondria they will have. Well, that makes sense. If you have a cell that's incredibly active, they need to have the energy to perform the action. One example is your heart cells. Your heart cells are some of the most active, consistent cells in your body. Hopefully. Because if they're not, you're in very big trouble. And so we're going to see really in our heart cells the highest percentage, the highest number of mitochondria to provide it with the energy it needs. Because every heart cell has to talk to every other cell and contract at the same time, the same strength every time. If we start getting guys going rogue, suddenly we have what I call spaghetti heart, and that is not good. We made nice, consistent, and hopefully it's being provided the energy it needs to do that, because if it's not, then, well, you cease to be. You end up having heart failure and you're gonna die. Now, we know that the mitochondria could have potentially been a prokaryotic cell because it has its own DNA. But is that DNA contained within a nucleus? It is not, just like our prokaryotic cell. It does, though, have its own DNA and RNA, and they're going to be located where the energy needs are the greatest. It's all kind of common sensey stuff right now. I call this stuff no duh. No duh. Well, if they produce energy, and there's an area of the cell that needs more energy, we're going to have more mitochondria in that area. I was a little disappointed. My meeting at Texas Burn Institute got canceled this week. They did not have any new protocols to go over, which I guess is good. So tell me what number we are looking at to identify the mitochondria.
9.
Yeah, number 9. Now, the other thing, I'm just going to stop your panic mode right now because I can feel butts puckering every time I put a picture like this up here. For your test, over chapter 3, I will not be having you label a picture. That deserves an appropriate amount of astonishment and gratitude. I will not be putting.
I was about to say, yeah, woo.
You are welcome. These are just for us in class to use for identification purposes. I'm not going to put this up on your test and have you list out numbers, which is which. This is introductory. This is just foundational so we can start building upon it into the systems. So the shape of the mitochondria, it's going to be kind of like this slug shape, they say elliptical. And we have the cristae, that's how you spell it, C-R-I-S-T-A-E. And this is where we are actively producing that ATP in the cristae. So obviously, mitochondria that are needing to produce more energy than others are going to have more cristae in them. If the cristae is what's producing the energy, then the more cristae that I have, the more energy that I'm producing. That's it. That's our mitochondria. Any comments, questions, concerns so far? Everybody okay? Everybody's on the bus? Excellent. Excellent. What group are you in with the dog breeds right now?
Hound.
Release the hounds. How many people are going to watch the dog show on Thanksgiving? I think everybody should watch the dog show on Thanksgiving.
I'm gonna try.
Everybody should watch the dog show on Thanksgiving. I might work with Ms. Regalia coming up with some sort of assignment about that, some sort of extra credit. Oh, I don't know how to prove that you actually watched it. I mean, I could say you have to let us know who won each best in group.
Question, if we do that, can we like maybe record it if we're not at home and watch it when we get home?
Sure. I haven't even talked to Ms. Regalia yet. I'm like taking over her class right now. I should probably talk to her about this. But I don't know, maybe.
Could bet on who wins.
Maybe, oh, that would be fun.
Yeah.
Right now.
Then you could just guess.
Yeah.
Started going. I don't know.
Well, what we could do, here's what we could do, Eric, and this is interesting. You've got, okay, Doug is finally back with us. We may not have to bet about which actual breed wins. What we could bet is which group does Best in Show come from. Because there are 5 groups, and you have the hounds, the toys, the sporting, the non-sporting. And then once those 5 groups have Best in Group, those 5 dogs compete for Best in Show. So there's 1 from each group competing. We could have a bet on what group is the Best in Show going to come from. Do what?
There's always the toys that win.
No. Last year, I want to say it was the Beagle that won. Time before that, we had the Old English Bulldog. First Old English Bulldog ever to win the challenge. There was one before that, we had a Doberman one year. We had a Boxer one year.
Wasn't there an Old English Sheepdog one year?
There was the Old English Sheepdog. I don't remember if that one won or if it was just in the final. But yeah, it's super diverse. It's not that the toys always win. It is different year to year because they have different judges year to year, which have different criteria for how they judge the animals. So I'll talk to Mr. Gillia. This sounds like fun. I might like to get in and get a little piece of this. I might get a little piece of this. We can bet test points or something like that. Well, not that you would lose them.
Okay.
No.
If I want to lose like 20 points.
No, guys, have we met? No. This would be like a gentleman's bet plus, where if you lose nothing, but if you win, you get something. No, I'm not going to be like, yeah, if you lose, I'm going to fail your next test. No, I'm pretty sure Mr. Hamilton would not approve of that. Betting on your grades. No, pretty sure that's frowned upon. But no, I will talk to her. I speak to her almost every evening because we're in the same classes together. So we're in 2 of the same classes together. So I talk to her almost every evening. Do what?
We can mention it more this afternoon too.
That no. Let me broach the subject. Let me do it. Let me do it because it was kind of my accidental idea. So yeah, let me take the fall for this one. All right. So ribosomes. Ribosomes are the most numerous organelle. Again, a great test question. Which of the following is the most numerous organelle in the cell? What our ribosomes do is they're kind of the little factories of the cell. They can be attached to the reticulum, the endoplasmic reticulum, and they can be static, meaning they don't move anywhere. Or they can be free and just floating around do-to-do. And what happens is we have the RNA, right? The body says, oh no, we need to make this protein. DNA copies it off. Sends RNA out, so this is now my strip of RNA. RNA leaves the nucleus, finds a ribosome. Ribosome clamps down and goes do 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 do. Little protein starts coiling out the top, releases, and then we send the protein, we package it up, we send it to the FedEx store, and we ship it out. That's what the ribosome does. It reads the RNA, creates a new protein. So they're really pretty great. They're what make the rough endoplasmic reticulum look rough. It gives them this little beaded look. This little beaded look. And we can also have them just out free floating do-to-do, just hanging out, waiting for some RNA to come and give them the opportunity to make some proteins. The endoplasmic reticulum is an extension of our nucleus. We have the rough endoplasmic reticulum, which is where we have our stationary ribosomes, making it look kind of bumpy. And here we have the smooth endoplasmic reticulum, which again is just an extension of the rough. And this whole thing is just an extension of the nucleus. So this is the creator of our ribosomes. The smooth endoplasmic reticulum acts very similar to our kidneys. It helps to detoxify the cell. And in fact, if you do things, terrible things to your body, like have too many burgers, right, and too many adult beverages, you will physically change yourself on a cellular level. Because it is the smooth endoplasmic reticulum that has to help filter out that toxin. And the more toxin the adult beverage, the more toxin you take in, the more smooth endoplasmic reticulum will be formed. And that's what they call tolerance. You know, when you are first turning 21, you have a sip of a beverage and you're like, I'm done. And then you become a seasoned professional. You know, 2, 3, 4, 6, 7, 8, and you're still doing just fine. On a cellular level, you have taken that smooth endoplasmic reticulum and you have now a lot more of it in preparation. Yeah, so then if you stop doing the beverages, stop doing the adult beverages for a while, and then, you know, 4 or 6 months later, you have one suddenly, oh my goodness, you have no tolerance whatsoever because it has gone back. But then once you start increasing the consumption, the smooth endoplasmic reticulum will increase as well. So kind of interesting how an outside force can literally change you on a cellular level. I find that kind of interesting. And time flies when we are having fun talking about beverages. Why does it always come back to beverages with us?
Because I need to.